on-off valve. Okay, sometimes you can on it, you can off it, or you can actually control the flow rate. This is a normal valve. Okay, this is the wheel, and you just rotate it clockwise, anti-clockwise. You either open the valve or close the valve. So the flow goes this way. The flow goes this way. Alright? And of course, what you call an angle valve actually is just a tap. Just a tap. Because the flow changes direction. It goes up here, it comes out here. So it's 90 degrees change. The angle is 90 degrees. Okay? Angle valve. Sometimes at 45 degrees, 60 degrees angle valve also has. Okay, let's come back to our solution of this question here. So now calculate the power required for a pump to deliver water through this pipeline. Okay, so the power required by the pump must be able to overcome the heat loss, the total heat loss. Okay, the power of the pump must be able to overcome the total heat loss. So, in this case here, we have, okay, that's here. The heat required, recorded H, is P over gamma. Okay? You must be able to overcome the pressure barrier. And power is given by this expression here. Usually, using capital letter S. Is equal to flow rate times specific weight times the heat. Okay. Now, what is gamma H? Gamma H actually is, as you know from the expression on top there, gamma H is actually your P, pressure. Okay? So S is actually equal to QP. Pump power is equal to flow rate times the pressure that the pump can produce. Okay, so what is P here? This P is actually your P1 gauge plus your P atmospheric. It has got to overcome the atmospheric pressure as well. Don't forget, when it comes out, it's atmospheric pressure. So it has got to overcome little atmospheric pressure. Okay. Now flow rate Q was found to be given as 7 times 10 to the power minus 3 meter cube per second. And your P1 gauge, have we found P1 gauge already? Do we miss? No, we jump. Okay, we jump one step too fast. So we haven't done the minor losses yet. Minor losses. We haven't done the minor losses. Okay, let's insert. Let's make it simple. Minor losses is equal to what? What's the expression? What's the equation here? It's K V1 squared over 2G. Okay? Now V1 you know, G you know. So what is this K here? So bear in mind there are 4 elbows, and each elbow has a K. So this K is called the loss coefficient, it's 0.5. And there are 4 elbows. So it's 0.5 times 4. Okay? Plus, what do you have? You have a group bar. Group bar is 1.5. Loss coefficient group bar is 1.5. Okay? 1.5 group bar plus the angle bar is 2 for its K value, 2. And D1 squared over 2G is 5.57 squared over 2 times 9.81. It straight away next line is your answer, 8.25. Okay? 8.25. Okay, so we have got here your P1 gauge. What was our P1 gauge? Okay, anybody give me your value of P1 gauge because we did not calculate HLN. Okay, P1 gauge here is equal to that's from your equation. Three, yeah? Okay, equation 3, do we put equation 3 here? Equation 3, P1 gauge is 9.8 times 10 3, bracket 33.72 plus HLM plus HLN. Okay, so this box 3 will be, in this case here, 9.81 with P1G first. Just to make sure that okay, what was P1 gauge? It was 9.8 times 10 to the power of 3, 33.72 plus, what was HLM? What value we calculated? What value was it? Anyway, I got 18.31, so I just put it there. Because this is obtained from the chart, then you do a calculation, so it's slightly different from your value, but it's okay. Plus 8.25. So in other words, it's 591.3 kilopascal. Okay, so P1 gauge is 591.3. 591.3 kilopascal plus what's P atmospheric? How many kilopascal is that? We approximate to 100. Okay, so that will be kilowatts. Okay, that will be kilowatts. So we just bear it in mind. This is our bracket to find our P here. Okay, P1G. So therefore, in this case, S is equal to, you use calculator, you get 4.8 kilowatts. 4.8 kilowatts. Okay, so that is the power required for the pump to deliver water through this pipeline. This has overcome the viscous friction. The pipe that will give you is main head loss, and overcome the obstacles. So all these fittings and the bars cause obstruction, it takes energy from the flowing fluid. So again, there's head loss. These are minor losses. So all these add up to form the total head loss. And the pump must have enough power to drive the fluid from the basement to the upper floor, and that is the pump power required. So you are going to size the pump. Make sure that your pump power is at least 1.5 times this. Okay? At least 1.5 times this. Okay? Don't put it exactly 4.8. Exactly 4.8 because in practice there could be some other factors coming in, and your pump may not be able to pump the water to the upper floor. Okay? Right. Let's look at another one, another example. You have here a pump is connected into a horizontal pipeline of 4.25 meter diameter. The pipeline has an overall length of 50 meter, okay, overall length 50 meter, and incorporates a globe valve. Okay, there's a globe valve over there, and two 90 degrees bend. So this is a bend here, this is another bend there. So schematic diagram of the system is shown in the figure below. Okay, this is an interesting question, pay attention. A performance relationship for the pump is expressed as this. Okay, expressed as this. So, expressed as this. Now, this is a very important relation there, where the head, the pressure head, is equal to 10 minus 1,000 square of the flow rate. Okay, where delta P is the pressure drop, Q is the volumetric flow rate for the pipe, and rho the density of the fluid. Okay, first, you have to calculate the average velocity of water through the pipeline. So for average velocity, you must have Q, you must have